We kind of got into this idea in topic 1.11, where we might have a function that has a particular discontinuity, and we might be able to define the value of that function in order to fill in or to remove that discontinuity. So let's look at that again and kind of formalize what we were doing there. Let's consider f of x. And we'll let f of x be equal to x minus 1 in the numerator and the square root of x minus 1 in the denominator. And in the previous topic, we said that this function, which is a rational function, is continuous for its entire domain. And so really we would look at the domain of this function and say, okay, the square root of x we know has to be greater than or equal to 0. But because it's a rational function, I also need to address the denominator being 0, which would occur at the point x equals 1. Square root of 1 minus 1 would be 0. So I know, just looking at this function, that f of 1 is undefined. And if f of 1 is undefined, that fails our first bullet point of continuity that says f of 1 has to exist. And so we're able to say just off of that alone that f of x is not continuous at x equals 1. The function can't be continuous if there's no value there. So the question that we have in front of us now is, okay, we know that it's not continuous at 1, but what if we could theoretically assign some value? So what value would we have to assign f of 1 in order to make the function f of x continuous across the rest of its domain, which would be from 0 to infinity? So I know I've got this issue at 1, but maybe I could fashion this in a way using a piecewise function where I could define 1 very specifically and have a situation where I was continuous. Well, in order for it to be continuous at x equals 1, then f of 1 would have to equal the limit as x approaches 1 of f of x. That would have to be true in order for the function to be continuous at x equals 1. So now let's evaluate this limit if we can. The limit as x approaches 1 of this function. So this is the limit as x approaches 1 of x minus 1 over the square root of x minus 1. And I should always, when evaluating limits, see what direct substitution gives me. It gives me 1 minus 1 in the numerator, which is 0. And we already know that gives me 0 in the denominator, so I get that indeterminate form, which means I need to apply some sort of technique to evaluate the limit. And because I've got a radical here in the denominator, I'm going to use the conjugate of this expression, which is the square root of x plus 1, in both the numerator and the denominator, and see if I can't algebraically work this limit out. So I still have the limit as x approaches 1. This numerator here, I'm going to leave it gross, x minus 1 times the square root of x plus 1, divided by, remember this comes out as the difference of squares down here in the denominator, so the square root of x squared is x, minus 1 squared, which is minus 1. And now I can divide off my common factor of x minus 1, and say this is the limit as x approaches 1. What I'm left with after these divide off is just the square root of x plus 1, which I can now evaluate as the square root of 1 plus 1, which is 2. And so if you look here at this long horizontal string here, in order to make the function continuous at x equals 1, I need to let f of 1 equal 2. And so what this might look like in order to make f of x continuous is I could redefine f of x as being a piecewise function. I could let it still be this piece of x minus 1 over the square root of x minus 1 for all x not equal to 1. But for x equals 1, what we really just solved for is I need to let f of 1 equal 2. And this function right here, if you apply our continuity definition, you would essentially get this work that's on this line right here. But you would find that this function right here is in fact continuous across this domain from 0, including 0, the left endpoint, to infinity, because we removed this discontinuity at f of 1.